I'd like to welcome you all again. There's still people logging on, but welcome, good morning. Today we're going to talk about visualizing 1 billion cells on an engineering desktop, but in fact it's my laptop.
That's right. Yeah, it's a pretty powerful laptop, but it is a laptop.
It is most definitely a laptop, and we'll kind of go through looking at that here in a second. But you know what, Scott? In looking at the data today, we decided that we're not going to look at 1 billion cells.
No, it's not big enough.
It's not big enough, and rather than try to rerun a smaller case, we've decided that we're going to run and look at 2 billion cells this morning.
That's right.
So today, just a quick overview of what we're going to talk about. And I'll wait for that to okay, so there's a couple of things we'll talk about this morning. First, we'll kind of highlight some of the things that are driving computational physics. Most of this is review for those of you who've had an opportunity to sit in some of our webinars in the past. We'll also talk about some advancements in visualization technology, and we'll talk about our new technology we've been researching for the past, well, about 20 months. Scott, is that about right?
That's about right, yeah.
And we've been looking at strategies for a long time, and we've kind of got to the point where we have a working new technology that dramatically improves performance for visualization.
Yes.
Okay. We'll also actually, this is going to be live. We're going to demo, we're going to load in 2 billion cells, not a billion. And one thing we want to point out as we're going through this technology is still, let's say, in flux. That is to say, we're still working on it. And although I haven't run into any issues with it in the time that we've been using it, that's not to say that using the alpha version might not cause some problems. So I just forewarn you, if for whatever reason it doesn't work for a particular file, which would be very unlikely, at least you understand it's new technology.
That's right. Yeah, it's bleeding edge at this point, but it's getting better all the time, getting more stable all the time.
And in fact, that's one of the reasons why we wanted to show it now, is because it is working. It's working to the point where we'd like to get some people to actually test it on their own data. And so part of being with us here this morning is you'll have an opportunity at the end of the webinar to sign up perhaps to be part of the technical preview, which would allow you access to this new technology, and you could do some of your own data to see if you realize the same benefit we are.
Mm-hmm.
So I think that Scott and I have talked about this quite a bit, and I decided last night that, boy, I just don't want to look at the same Moore's Law curve again. So I thought we could take a look at a couple of things. Number one, as you might have seen yesterday in the news, or a couple days ago, that China now finished their supercomputer, and they're currently number one of the known supercomputers.
Yeah, that lasts a month or so, and then somebody else takes over the crown. Yes, but of course, this is all being driven by Moore's Law, of the fact that the size of the transistors or the components on the integrated circuits is reducing, halving basically every 18 months. So you double the number of transistors you can get on a certain size of integrated circuit. And the result of that has been a continual improvement in performance. For a long time, it was continuing through higher clock rates, and now it's primarily through parallelization, multiple cores.
And this is extended to the desktop now. In fact, yesterday we were talking about Intel's new chip, which, as I understand, has 12 cores.
12 true cores, 24 virtual cores, and you can put two of them together in a workstation. And so you can have 48 virtual cores in your workstation. That's a lot of cores.
That's a lot of cores on your desktop. So parallelization is still very important.
Yes.
So that probably is going to be the case for as long as I'm involved in engineering, I'd assume. So in that context, then, people have been driving complexity in numerical simulation for years. And in fact, over time, the problems, both size and complexity, has grown with Moore's Law.
That's right. one of the issues is that in fluid dynamics especially, but also in other areas of simulation, the scales, length scales involved in the solution are so varied that you really can't have enough grid to resolve them all. That's why there are turbulence models or large eddy simulations, because you're ignoring some of the length scales. And ultimately, you want to be bringing in more and more length scales, which means you have to have much larger grids. So in effect, we've been tracking this for 15 years now. And in fact, the typical grid size from a CFD solution has grown with Moore's law. It's doubled every 18 months, and it continues to do so. Every time an engineer gets, or an organization gets a new supercomputer, the grid sizes go up.
Yeah. And then, so the natural consequence of that is that the signal-to-noise ratio, that is the amount of useful information in a large simulation, actually goes down comparative to the data that's probably not as useful. So that's a new problem people are having to deal with, is I've got so much information, I've got to quickly analyze what pieces of it are interesting, and we'll talk about that in detail here in a second. So that complexity continues to grow, and what we've been working on is perhaps two different strategies. The strategy we're going to show today is more related to an individual assessment of a given solution, but it can be extended. So the performance gains that we're going to talk about this morning can be extended to sets of solutions or unsteady solutions. And as we'll show, these performance improvements are very significant. And so if you apply them to a set of solutions, in principle, one could analyze 100 million cell models on a laptop with, well, I guess I've run it with 4 gigs of RAM.
Yeah.
So I suspect you could run with less. But in principle, if you assume each one's probably going to use less than a gigabyte, you might be able to run 10 of those at a time. If you process that much data that quickly, you're going to spend more of your time doing actual work and less of your time looking at the screen and waiting for something to happen.
And that's the nature of Tecplot Chorus is for, as you're seeing here, is our product for visualizing collections of data, large collections, related collections, usually from a parametric study or of some sort. And so you have, as you said, maybe 100 or 1,000 solutions, and you create a new view that you want to look at in your data, and you want it to be reflected in all 999 remaining solutions. And so Chorus then will go out and do this, and frankly, it takes a long time unless you are very smart about how you load your data.
Yeah, and we'll talk about that in detail. So we don't want to spend too much time on choruses. That's not the primary driver here, but it's worth pointing out that the use of parametric analysis has become very common. People are applying it to robust design, statistical engineering. We're seeing people doing comparative analysis, looking at aggregations of statistics across sets of solutions. And it really leads to an enormous amount of information, thousands of solutions. And so we're not going to talk about that here today, but an upcoming webinar will show how a combination of this new technology and the existing Tecplot Chorus technology can be very powerful for analyzing sets of solutions. Kind of move on.
Okay.
So if we kind of walk into the, many of you have seen this before, but this is the data processing pipeline. And if we move from where the solution files are, and they don't have to be local, they could be local, in which case bandwidth wouldn't be necessarily a rate determining feature. Then there's the CPU, GPU, depending on how the data is analyzed, and ultimately the rendering. And in principle, we've been talking about this for some time, but the GPU, CPU is doubling about every 18 months.
Yeah, that's Moore's law.
Moore's law, and it's consistent. The bandwidth, although not linear in that we don't start off and then 16 months from now we'll incrementally get to the point where it's twice as fast, but about every 16 months there's improvements that give us about a 16 or a doubling of overall network bandwidth.
Yeah. And that usually actually occurs in orders of magnitude, at least on local area networks, right? You go from 100 megabits per second to a gigabit per second to 10 gigabits per second. And beyond. And so that's right. Yeah, I mean, it doesn't happen continuously, but on the average, that's about what it does every 16 months or so.
And what we've seen, and actually, we had a conversation with a group recently who they just can't write the data fast enough.
Mm-hmm.
They were saying, well, hey, I can't. Not only can I not read it, I can't even write it. But the problem we have is that loading data, that is the I/O from the disk, whether it's an array, whether it's a parallelized file system, whether it's a local solid-state drive or a traditional drive, it's only doubling every 36 months.
Yeah, the 36 months is Kreider's law. And that's actually at the at a spindle level. It's doubling every 36 months. So in principle, if you could exponentially grow the number of spindles you had in your parallel file system, you could keep up with Moore's law. But you can't do that. Exponential growth of hard disks is not feasible. And so in the end, what's happening is you get this redshift, is the term that a lot of people use, where the hard drive is becoming the bottleneck more and more as time goes on. It's the bandwidths that are getting separated in a way that it makes it very hard to get your data off the hard disk in a timely fashion. And so you can see here, this is Kreider's law, and the top one is Kreider's first law, which is disk capacity is doubling every 12 months. So capacity is fine; it's doubling, faster than CPU performance. So every 12 months, they come, you get twice as much data, but it's not, you can't read it as fast as you could before. I mean, for the same file size, it's faster. Mm-hmm. But if you tried to read the whole disk or copy a file, off the disk, it's slower. And in fact, if the file size is only growing with Moore's law, which is what we know is happening from studying this for 15 years, that is also growing faster than the I/O performance. And so it's taking longer and longer to load our CFD files from the hard disks.
And so that was probably the main driver when we started looking for technologies. And that's not to say, and I recently wrote a blog about this, but there's been a tremendous investment in strategies to leverage highly parallelized clusters for visualization. That includes parallel rendering, of course, parallel data loading, and there's a number of things that people have been doing on the cluster to try to make it so that they can visualize very large data. And there's a lot of people who have access to those resources. Yeah. But in my experience and what I've seen, the number of people who have access for their day-to-day engineering work to the large HPC facility is small.
Yeah.
For the most part, they end up either running in batch mode because they can't actually get the head node, or they copy the data local and they try to do the processing on their desktop or their workstation. So in a way, those great improvements, they're only improvements if you have access to very large computational resources.
And from a trend point of view, if you go to a parallel file system, a parallel machine, and do parallel reads, in the end, you're still going to be hit by Kreider's law.
Right.
Because it'll be dramatically faster now, but that redshift is getting worse as time goes on.
So that's actually a good point, Scott.
Yeah. So the consequence of this is that you can look at the time it takes to read data from the hard disk, transfer it across the network, and then render it. And in this analysis, we're actually ignoring the rendering side because we've really what we haven't talked about is how the graphics processors have improved, and they're just improving it very fast. So if you just look at the time it takes to read it and transfer it, you can see that because the file size is increasing, the time it takes to read is increasing. And it's increasing pretty dramatically over time. And the time it takes to transfer it, because the networks are actually improving pretty rapidly, is reducing. Now, some people say maybe it's not reducing, maybe it's pretty much flat, maybe it's doubling every 18 months on network performance. But either way, you get the same sort of analysis. And in the end, you get this point, this minimum point on the time. And you can see here that our analysis says that's somewhere in that it's passed.
Right.
And that from now on, for these two particular cases, the time it takes to visualize something is actually going up. And this is just about reading the data and transferring it. This is nothing about parallel extraction of isosurfaces or rendering at all. I mean, this is just the reading time is actually increasing as we go forward.
And there's part of the strategy people have been using, and a number of other applications have tried, which is basically, I'm going to guess going into my simulation that this is what I want to look at, and so I'll only extract that feature.
Yeah.
And although that approach is fine, it's only fine if you're absolutely certain that you're choosing the right feature. And what we found is that often that's not the case. That in fact, when you start off, you think that, oh yeah, well, I know exactly what I want, but if you miss, going back and having to regenerate the data can be another heavy investment. And so we're looking for strategies that don't make it so that you have to do that, so that you can get the same performance that you would get by looking at only the features, but now you can do it with the complete volume. And of course you can always extract it, but we'll talk about that in detail. So ultimately then what we'll talk about is to reduce this bottleneck, to overcome the redshift, one needs to reduce the amount of information needed and read from the disk. And we'll talk about Subzone Load on Demand, which is a technology that we've developed over the last 20 months or so to help address this.
And the key here is that it must scale sublinearly. This is about sustainability, right? We want our improvements to be sustainable over time, in spite of this redshift. And so you must scale the amount of data you read sublinearly. You double the file size, you can't double the amount of data you read.
Right.
And that was the goal here. And it basically you do it by indexing the data and then loading only the data you need. It's a fairly simple concept.
So conceptually, although many of you have seen this before, Subzone Load on Demand, and this is a simplification obviously, but basically what it says is that for any particular feature, that could be an isosurface, a slice, a streamline, a contour line, that feature only goes through a subset of the total volume. And the idea is that if you can index appropriately, one can actually load only those zones of information, the information around where that line actually is going to be drawn. And as a result, the amount of information you have to load, again, depending on the size of the data, can be substantially less. This case, it's 5/16 of the data, but again, this is an extraordinarily simple case. It's really not reflective of what's actually happening. Here's a better example of showing you what those subzones might look like in 3 dimensions.
Yeah, it's kind of hard to see this. It just looks like the one on the right is a little fuzzy, I'm sure, on your screen. But what that actually is little blocks of data that are spanning the isosurface. And so you can see that there's that it's actually a very small part of this overall volume, which is the cylinder you can see outlined on the left. And that's how it works. It loads a very small portion of the overall volume.
So we want to get into the meat of this, so we'll try to pick up the pace a bit so we can actually show you this. So this can be extended again to unstructured data. So today we're going to look at a number of test cases. We'll start by looking at a relatively small case. This is a landing gear. The data came from CFD++. It's relatively old, to be honest with you. We've had this data set for, gosh, how long? Maybe 10 years.
Yeah, it's been around quite a while. It's a nice data set, but it's not very big.
And we wanted to show you this because in principle, this approach is great for large data, but it has to be pretty good for even small data. Otherwise, there won't be enough of a reason to make the investment in this new strategy. We'll also look at a case that came from Cobalt. This is a pair of helicopters flying side by side. And last, we'll look at, well, 3 cases, so I guess it's not last, but there's a trapezoidal wing. This is from the High Lift Prediction Workshop, and it's 208 million cells, as well as we doubled it to make it 416 million cells. And last, we'll look at a 2 billion cell model.
Mm-hmm.
So, Scott, do you want to?
Sure. This is actually this synthetic data that we've created just to test the scaling for this new technique. So you can see that that the lines on the right, the top one is for time, and so the time it takes as you increase. This is an exponential scale, a log scale now on the size. That's the horizontal scale. Vertical scale is time. The time does increase, but it does increase sublinearly. That was our goal. We wanted it to be sublinear. Now, if you actually were to look at the time it takes if you're reading the full volume, it looks like a hockey stick, right? It's just going straight up. It's right. Growing exponentially. So if you had both of them on the same plot, this would just be right on the axis. Horizontal axis, basically. The other key here is that it uses a lot less memory. Yeah. We've gone up to 10 billion cells in this case, and it's using only 2% as much RAM. That's, I believe, at the 2 billion cell case, as when you load the whole data set. At 10 billion cells, the truth is you can't load the whole data set. On any machine we have in this office, it would take at least about 200 gigabytes of memory on your computer.
Unfortunately, we don't have.
We don't have that. So I know some people do, but we don't. And it does indeed scale on the order of n to the 2/3. So it's sublinear. Yeah. Order n would be linear, and that was our goal. So
how this works, and again, we're going to go through this somewhat quickly, but in principle, one has a CFD solution file that either came from a solver, or your solver may use the Tech.io library we provide, and this is freely available to anyone, that would write out this new file. Or you can use Tecplot 360 to import the file and export it as a Subzone file. Or we'll have a compressor and translator, which would basically take a solution, compress it by up to 40%, and write it out in this new file. Our intention is to have a reversible translator that would allow you to go back and forth from, say, common formats like CGNS and Plot3D into this new format.
Yeah, and then the key to that is it does compress it, especially for finite element data. It can compress it up to 40%, so almost a factor of 2. Yeah, pretty significant reductions in size.
Certainly, when you start thinking about these files they're in the 20 to 120 gigabytes. Some of them, and for the billion cases, can be up to a terabyte. That's significant. So.
Yeah.
Okay, so the cases we're going to look at, the first case we'll look at is a simple landing gear configuration. It's a finite element mesh. It's about 1.12 million cells, and the solution file is about 148 megabytes in size. Very small, but the idea is to show that you can use this with small cases and still see a net benefit. The second case we'll look at is 2 helicopters flying in formation. It's a finite element mesh. It's about 8.2 million cells, and the file is about 640 megabytes. Again, this is a relatively small case used just to show you kind of that you would see a benefit even in small cases. The next 2 cases, we're not going to talk about this in detail. I think we'll come back to the results after we actually show you in detail. But to point out that you can load it today. It takes about 20 seconds, and we'll show you with the new technology it's about 2 seconds. The third and fourth cases are around the trapezoidal wing from the High Lift Prediction Workshop. And they're both finite element bricks, tets, and prisms. And they're 204 and 408, but it's actually, I think if you look at it, it might even be a little bigger. It's 208 and 416. And the solution files are nominally 13 gigabytes. And so we've talked about this in the past, and we're going to show you that in Tecplot 2013 R1, it's about 210 seconds, and it uses about 19 gigs. We'll show you that you can load some of these things in the 2 to 4 second time frame and use less than a gigabyte of RAM. And then the full trap wing, which is the 416 million cell model, I can't load it on my laptop because I only have 32 gigs of RAM, so I can't show you that one, but I will show you that you can load it using the new technology and use less than 2 gigabytes of RAM. Finally, we'll look at the 2 billion cell model, and again, we don't have examples we can show you much because they're impossible.
Yeah, we have one machine in the office that can load the 2 billion cell example on in Tecplot 360 2013 R1, and that is a 96 gigabyte machine, and it just barely loads it. It's pushing the limit, and so if you go beyond that, I showed you already a 10 billion cell result in the scaling. Yeah. I mean, that's impossible. So in any machine in our office, and probably most offices, frankly.
So from that standpoint, this new technology makes the impossible possible, at least for me. And so we're going to go ahead and we'll get out of PowerPoint land for a moment, and I'm going to wait for this to update. And we'll start by looking at, this is the data, and I'll show you the data set. And we're going to actually load these so you'll get an opportunity to experience that load time. So if you go to dataset info and look at the data set, you can see that this is 209 million elements, 231 million points. Okay? And you can see that the performance on screen is obviously quite snappy. And the amount of memory that's being used by Tecplot 360 today, or right now, is 863 megabytes. But you don't want to see this. We're going to actually get to this one, and we're going to march up from the small stuff to the big stuff, and we'll go ahead and do that. So let's we're going to start by the landing gear case, and a couple things to point out. You can see this. There is a Subzone load on demand file, and then there's a tree file for each variable, and that's basically the indexing strategy. You'll also see there's a PLT file, and there's a landing gear, the full PLT. This is just the surfaces. So this is what we're loading, and we have some layouts. So let's first go back. What I'm showing you from a version standpoint is Tecplot 360's next release. We're working on it now. Some people are actually part of our beta program, but this is a complete redesign of Tecplot 360. with a focus on making it so you don't have to learn or relearn anything. Most of it's going to be what you're used to. But we made some improvements along the way to make the usability even better, because we know that you may not use post-processing. You'll be doing CFD maybe for 2 weeks, and then you might take 2 months off, come back to it. We wanted to make that transition easy. So we really made it focused on ease of use, stability, and performance.
And while you're loading this, it also is faster, even without the Subzone load on demand.
Absolutely.
This is up to twice as fast as the previous version of Tecplot 360.
So I'm going to just open up that case that we talked about. This is a landing gear, and we're going to generate a series of isosurfaces. And we'll go ahead and load that in. Now this is in Tecplot format today, and you see it takes about 3.7 seconds to load. So that's in our current format. Still pretty fast.
Standard format, yeah.
Let's see. Okay, good. Waiting for it to update for you. And we'll let it update again. Okay, let's do the same exercise, but this time, actually what we'll do is we'll start fresh so that it doesn't have any caching issues. And let's go ahead and load that. Same thing. We're going to open the layout, but this time we want to use the Subzone strategy, and you can see that it loads in less than a second. So it's, even for this small data case, it's 6 times faster.
Yeah, and that may not seem like much, but remember, if you're doing this in Tecplot Chorus, that's a 5-second advantage over 1,000 cases. So yeah, it becomes a significant amount of time.
Absolutely.
Yeah.
And then that's something that when we look at it, and again, if you're looking at multiple files, that can be extraordinary. Or if you're looking at unsteady simulations and you wanted to animate through 1,000 of these,
Right.
well, it's going to take you 500 seconds, and with Tecplot 360 today, it would have taken you, well, a lot longer. So, all right. So let's move up to perhaps a more representative data file. That is the helicopters. And we'll go ahead and start by profiling the load of the actual PLT format. And so what we're looking at here again is an isosurface. And it takes a second to load.
This is an isosurface of lambda 2.
Sure.
So this is one of the standard techniques for visualizing vortices. And so, yeah, it'll take a little bit of time to do this with the standard Tecplot. Go ahead.
So I'll let that update on the screen for you. So I disregard all the information below here. I think the important thing to point out is it took 22.71 seconds to load, which isn't a long time.
No.
But at the same time, if you're doing this day in and day out, it gets old. So let's go ahead and load in now the Subzone file. And okay, so there it is. Same file. Now we're just using the new strategy. And we're going to profile that. And so in this case, it takes 2 seconds.
Huge difference.
Huge difference, and it's what you always wanted. I mean, that's the point of all this, is that ultimately, as an engineer, you don't want to spend any time waiting for things, because that's not productive time.
No, and that 18 seconds is time to start thinking about, what you're going to do, have for dinner or whatever. It's a distraction. So this helps you keep focused.
Absolutely.
And this is not a huge case. This is probably less than average at around 10 million cells. But as you see, as we go up in size,
yeah, it gets more pronounced.
It just gets better. Yeah.
All right, so we've looked at a relatively small case, or a very small case, a relatively small case, and now we're going to look at one of the bigger cases.
208 million cells. So this is maybe a little above average for our customers that are running CFD cases, but not much. I mean, this is a not uncommon file size.
Now, let's double check our timing to make sure we have time for this. Okay, we do. So what I'm going to show you is what has caused me, at least, to drink more coffee than necessary. And those who know me, I like coffee, but because things take a long time,
yes,
I end up getting more than I need. So this is, I'm just going to load in the geometry, the volume, and just take a slice. And we're going to load this in Tecplot format. Now, I don't think you can hear it. You might hear the fan in the background is my laptop. It's basically in complete lockdown mode, and it's loading in the data, and it will take a while to load.
Yeah, and this is when, about now is when you start thinking that you want some more coffee.
Or you start thinking, well, I don't want to do this again, so I'm going to just run everything in batch because,
Yeah.
Who has time for this?
Right. So what it's doing is it's loading. It's the previous Tecplot, or using the PLT format. It doesn't load all the data.
No.
It loads the data that it needs, but it loads the granularity is at the zone variable level. So it'll load X and Y and Z for each of the zones that impact this slice, and which is in this case all the zones.
Right.
Now there's all these other variables that it doesn't load, so it's better than it could be. And frankly, this is the case that we've shown it's twice as fast as Tecplot 360 2013 R1. So we've sped it up since the beginning of this year by a factor of 2, even with the PLT files. Right. And you'll get similar advances in performance with the other formats as well, CGNS and Plot3D. But it still is taking a while. Now this is going to should take about 2 minutes.
About 2
there
minutes.
It is, yeah.
So it's about a minute and 22 seconds or so. Now, this is the other thing. I mean, this is not productive time. And if I have 100 of these, this is all bets are off. That's 100 times 100. That's 10,000 seconds. That's a lot of time. I probably wouldn't want to be around for that. So that was one of the reasons why we invested in this technology. So let's go ahead and try this again now with the Subzone load-on-demand technology. And I'll wait for it to update. I know that the bandwidth between my computer and the internet's not infinite, unfortunately. Not as fast as it could be. So let's go ahead and do that same profile now. We're going to profile the loading of that. And in this case, we're going to use our new strategy. And so as you recall, the other one took, what did we say, 102 seconds?
102 seconds.
And this one took 5.62 seconds to load. And if you take a quick, I'm not great at math, but that's a lot faster.
It's a lot faster. And the other thing is, you look at the amount of memory, peak memory used. It's less than a gigabyte.
Right.
We didn't look it out in the other one, but I think
it's 19
gigabytes.
19 gigabytes.
So that is in some ways even more significant, because if you have an 8 gigabyte computer, and I know some of our customers still do, mm-hmm. You can load it easily on this. You can load you can load 8 of them on this.
Right. Before
you couldn't even load one. So big difference.
Right. In fact, yeah, with an 8 gigabyte machine, this is not going to work for you. So, once you have the data in, of course, you can do all the things that you do in Tecplot. When you want to create an additional slice, which is a common question people ask, is, well, wait a minute, that's cool, but you didn't load all the data. So if I want to generate another slice, how does it work? Well, again, it's going to go back into the file, and it's going to take only those subzones and create a slice. So that second slice will take you about 4 seconds, whereas if you loaded it all, it would take 2 seconds. But my contention is 2 seconds or 4 seconds is not a huge deal. We're still talking about just a few
not
seconds.
Compared to 6 seconds versus 2 minutes.
Right.
Right. So you would have to be sitting here and moving the slice back and forth for a very long time before you'd see before that make it worth loading all the data.
Yeah. So there we go. We've done up to 200. Again, the results are more significant with the larger files than they were with the smaller files. And now we're going to look at the 416 million cell model.
So this is actually the same data set, but the other one was it's a symmetric flow, so they only did half of the plane.
Right.
Now we're doing the full plane. So this would be more representative if, for instance, somebody was doing this airplane in a crosswind, where it's not symmetrical flow.
Now it's important to point out that I was unable to load this file if it was just in Tecplot format. We do have this also in a couple of other formats, including Insight, and I can tell you that no matter what format on my machine anyway, I can't load it, I just run out of memory. And so once you run out of memory, it starts to swap from the disk, and it's just all bets are off. So got to have a start point of, I can't show it to you today, but just assume that it would be the rest of our time together. And so we're going to go ahead and load an isosurface. And unlike a slice, the isosurface has to be a little smarter about how it goes through the data file. And actually, let's try one other thing here. I'm going to show you exactly how to load it so you get a sense of it, and then we'll create a layout. So the first thing that one would have to do is load in the scplt file, which is the Subzone file.
So this is just another loader. You just go and when you select your loader, you select the scplt loader.
Now, one thing to point out is it's instant because it's just the volume data, and it's not going to show anything because you haven't actually dropped in a slice or isosurface. Mm-hmm. Then, of course, you probably want, in this case, I'm going to load in the surface files, and the surface files aren't small, but we can load those in as well, and we'll just append them. And so now what we're looking at is about, how many triangles? 10 million triangles?
Yeah, there's 10 million triangles on the surface, so it's substantial.
Right.
It takes a few seconds to load that. actually it probably takes longer to load the geometry in this case than it does
The volume.
to load the volume cells for the slice.
Yeah.
So you can see it's pretty small. It's the
Yeah, it's way in there. We'll kind of zoom in here so you can see it. So there it is, right there. Okay. So there's our model. And I'm going to reset the orientation axis so that we can rotate this around. All right, and now what we'd want to do is basically look at the isosurface. So we'll look at an isosurface of, say, -2.
Right, so here we're looking at coefficient of pressure. So -2 means it's a low pressure area. So you'll see it actually will show a low pressure region on top of the wing.
Right. And I would have shown you this as just a layout, but I wanted to give you a sense of just, what would it be like to do the process.
Yeah.
It's important to point out that isosurfaces are a little longer. I think it takes about 20 seconds. So there's our layout, or there's the layout, the final thing that we want to look at. So if we wanted to get a timing, we'll go ahead and save this layout, and perhaps we'll just call it ISO and overwrite. Okay. So if we then just go back to start point, we'll use our profiler, we'll grab that model, and we'll go ahead and open it. And again, it's going to go through, it's going to load the surfaces, it's going to create the isosurface, and we'll get a timing.
And it's important, as you're looking at these timings to realize that it is actually, this is the time to actually load the data and to render. It's the whole thing. And you're starting with 10 million surface cells, and then you add in another probably comparable amount of triangles in your isosurface, and it takes
about 24 seconds. And a key thing to point out here is it's using 3.7 gigabytes of RAM.
Yeah.
Now I loaded this file on a machine that we have, an old machine that's floating around. It's a Windows 7 machine with Core 2 Duo, so it only has 2 cores and 4 gigs of RAM. And I was able to load and process this data meaningfully. I did a slice, I think, in that case, which is just insane. I mean, the fact is that this strategy allows you to use old hardware to look at very large cases.
Yeah.
So I guess as the final step in the process before we just open it up to Q&A is we're going to load in the 2 billion cell model. Now, mind you, there's no geometry, and unfortunately, we don't have a lot of data from customers that's 2 billion cells because they don't want to copy it and move it around. It's just too big. So unfortunately, I don't have any models that are that big.
If you have some you'd like us to try,
we'd be
happy to get some.
So let's take a look at this. We'll just look at an isosurface, and we'll hit open. Now, again, this would be impossible for all but one machine in our office.
Right. And that machine has 96 gigabytes, and it starts swapping as it's loading this.
So, again, this took 9.8 seconds, and it looks like it's using slightly less than 2 gigs of RAM. Mind you, there's no surfaces, so that's one of the reasons why it's so fast. Just quickly, if you go to dataset info here to get an idea, this is 2 billion elements that we're looking at. So this is very fast in comparison to other strategies. So
and it's interactive rotating, so it is.
Now, mind you, if we wanted to, remember it's 10 seconds. Okay, well, what if I want to look at 0.5? We can do that as well. Again, you're going to have to pay the 10-second penalty.
Right.
But it's still only 10 seconds. We're not talking about 20 minutes. So we'll let this load. Okay. And I don't know what that isosurface looks like. I guess it didn't redraw. But the point is that I interrupted it. So you can see then that this strategy leads to some pretty impressive results. Let's get back into our presentation. We're going to open this up to Q&A. So let me see where we're at. Okay, so just real quick, we showed you can load these large or these relatively small files, the 1 million and 8 million cell models, and on average they're about between 10 and 20 times faster.
Mm-hmm.
For the 204 million cell model, that's where you really start to pay that tax. And we've actually done some benchmarking against competitive products on the market, and that will remain nameless. But in fact, our strategy, just the Tecplot 360 2013 R1, for a machine with the data local, we're comparable or faster in all the things that I've shown you. So the fact that we're 20 times faster than our current tool suggests that we should be much faster than many of the tools on the market today.
Yeah, absolutely.
And the last thing, of course, is that we actually have a 2 billion cell model that we loaded on my laptop, which is in many ways just insane, to be honest with you.
And 2 billion cells, frankly, most competing products would say that's when you go to the parallel machine. You have to go to parallel. Just to get enough memory, you have to go to parallel. And you know, and with all the associated costs and complexity of you know, allocating the nodes and running on a parallel machine. So this really makes things possible that just weren't possible before.
So we're going to open it up to questions here in a second, but I think it's probably worth just highlighting some of the key conclusions. And so far, we've seen a dramatic reduction in memory. And actually, the memory reduction is probably an area where we'd want to make sure we highlight, because yes, the speed is good, but more fundamentally, we're going to reduce the amount of memory you need. And that has a huge impact, because not everyone gets a refresh every 12 months to a new machine. So this really, you're talking about between 2 and 25% as much memory. Of course, that depends a lot on the case. And the scaling we've shown is actually on the order of n to the 2/3.
That's for isosurfaces and slices. We haven't talked about stream traces here, but our experience with the stream traces is that scaling is on the order of 1/3.
Right.
Now, Tecplot stream traces are pretty darn fast to begin with, but this is even more dramatic with this new technology.
We didn't show it here today, but we're also working on a Subzone server, which is like a client server, which would allow you to run in client server mode from your HPC facility back to your client on your local workstation. So our intent is to have something to show on that perhaps in the next month or so, and as soon as we do, we'll have another webinar to talk about that strategy. The downside is you do have to convert the files to this new format. The upside being that the new file format is about 40% as large as the original file, which means you get a nice compression. And with TechIO, you can do this directly from the solver, so that should make it a little easier. So we're going to open it up to questions, and I want to, while we're going through questions, just very quickly, if you're interested in trying this technology with your own data, we would love to add you into our beta program, and you can go to the link below or just go to our main website and you'll see beta test program, click on it, sign up, and we can get this in your hands. Or if you want to talk to me directly, my email is here. It's d.rittenberg@tecplot.com. You can call me. This is my landline number, or you can call the main Tecplot number. My extension is 271. Be very interested in talking with you, but certainly email is fine as well. So with that, let's go ahead and open it up to questions. We do have time for quite a few here. Okay, and we already have some questions, so let me get this a little larger so Scott and I can read it. Okay, questions. There we go. All right. So there are about, okay, there's a number of questions already. Okay, so let's start with how long does it take to generate the SCPLT files? John, that's a great question. In the current alpha that I'm showing you, we haven't really spent any time on optimizing the write, but we are working on that and parallelizing that. So, Scott, you want to talk about that?
So it does take a little while. Of course, it depends on the size of the file. The 2 billion cell case takes more time, obviously. Just reading the data takes quite a while. So, I mean, right now, it may be for 2 billion cells, it may be measured in an hour or two. Yeah. But for the smaller cases, it's pretty snappy. In the future, we expect that the write time is not going to be that significant. So.
No, and again, that's an area where we're going to invest energy. We just haven't done that yet. Okay, so are you loading and computing the isosurface? Yes, we are, Stuart. We take the data. We're actually using the calculation of the isosurface and then using that to go into the subzones and pull out the right information. I don't know if you want to talk about that.
No, that pretty much covers it. So the process is you go into the tree file, you query it, you say, which subzones do I need? It goes through a tree to figure out which subzones it needs based on the isosurface value or the location of the slice, and it just loads those things, and then it generates the isosurface slice on the fly as it's loading them. So it's all done in that 10 seconds or whatever that we were looking at. It's all done.
Right. Another question was, what kind of video card are you going to need for this? To be honest with you, I mean, the only video cards that I'm aware of that aren't optimal are the integrated IBM ones. Outside of that, I think the rendering is really not the issue.
This is pretty much independent of the rendering. Now, if you have a slow card, we have strategies within Tecplot to handle that.
Right.
Where you can approximate the grid. It's not ideal. You'd love everyone to have a great card, but we understand not everyone does. So in that case, you turn on grid approximation, and it will you'll be able to rotate a coarser grid, and then it will render once you stop rotating, and it'll be useful.
And one of the things that I've run into personally was at home, I have a really fast video card, lightning fast, because it's a gaming video card. But here at work, my laptop, the video card's kind of an older NVIDIA mobile card, and it's not very good. Yet I'm still able to do the things you see here today. So,
yeah. The truth is, it's usually not the rendering anymore.
So the next question was more around Tecplot RS. Will we be integrating this technology into RS? Don Roberts, who is the product manager for Tecplot RS, and I were talking about this yesterday. Mm-hmm. And long term, that's the direction we're going to go. So that's where we want to get to. So there's some strategies that might help with RS as well. Okay, there was a question here. All right. Will Tecplot 360 run on a cluster with CPU and GPUs in the near future? We talked a little bit about that yesterday as well. We had kind of a technology planning summit. We haven't really made the investment, but that is in our plan to look at ways to leverage a GPU.
Yeah, I guess strategy-wise, one of our strategies is to make it so you don't have to use the cluster. But there are scenarios where you want to use the cluster. For instance, if you want to just generate your visualizations on the fly as you're running the case. And so certainly it's in our plans to do that in the future. Mm-hmm. It's not something we're working on at this moment.
Okay. Now the other thing that there's a couple questions about, well, what happens if it's unsteady? Well, that's really where this thing is going to be wonderful. And in that case I showed you in particular, for example, the 1.12 or 13 million cell model, if it's unsteady, in principle, you're going to get that 0.45 second per time step.
4.5 second, yeah.
Was it? No, 0.45.
Oh, okay, 0.45, yeah.
In the new format. Yeah. So it's going to be great for unsteady results. So we're excited about that.
Yeah, it's 5 times faster, and yeah, so you get all the benefits in unsteady as well.
Yeah, and let's see. Can or will the indexing files handle deforming messages or message which change from one time step to another? Chuck, that's a good question. In principle, it should, so that really shouldn't pose too much of an issue.
Yes, it will. It means that the advantage of a mesh that doesn't change is you can use the same index file for multiple time steps, but if it does change, you just write a separate index file for each time step, or you do separate indexing for each time step. So yeah, that's not a problem. You'll still get the benefits.
we have time for maybe one or two more questions, so let's see. Did we catch all of these? Okay, we've got, okay, there was a couple of questions about the video card. I think we already hit that. Okay, there's a question about, so can this be done kind of out of core, so to speak, can be done in batch? The short answer is the file conversions can be done in batch. The strategy that we'll have at release will allow you to run out of core potentially, so you'll be able to kind of process these large files without having to load them into Tecplot.
Right.
But the intent over time will be to make it so that major solvers will write out in this format, and so you won't have to worry about it.
Right.
So. Okay. All right. Let's see. There looks like, okay, if there's no other questions, well, Scott, thank you for joining me this morning, and thank you to everyone who sat in. Hopefully this was educational, and you can see the progress we've made. Again, if you are interested in participating in testing of this new technology, please contact us. You can contact me directly, and that's drittenberg@tecplot.com. There's my phone numbers as well. Or please just go ahead and pop over to our website, click on Become a Beta Tester, and we'll go ahead and get you set up so you can experience this new technology. And with that, I'd like to thank everyone again, and thank you, Scott.
Thank you.
Our next webinar will likely be in about a month, where we'll talk about some of the technologies around the client server.
Looking forward to it.
Thank you again.